Alright, nerds. So today we're going to look at a bit more of our acidic environment, and we're going to start and define what an acid is and how they work. And we're also going to look at how it is we measure it. What actually is the pH scale? And then in our next lesson, we'll do some calculations on pHs as well as a couple of other things. So, what's the point? Basically, by the end of this, you should be able to define an acid according to the Bronsted-Lowry theory. Now, we're not going to go deeply into that theory today, but you should be able to explain what an acid is. And these are our two guys. So we've got the Danish man, Johannes Nicholas Bronsted, and the British man, Thomas Lowry. Now, we want to basically also be able to name and draw the structure of several acids listed. That's the ones on the previous page. And we also want to be able to correctly use the terms weak, strong, concentrated, and dilute when we're talking about acids. So you need to remember, however, that an acid in water creates a hydrogen ion or a proton, or alternatively a hydronium ion. That three should be a little 3 down there, obviously. And it will neutralize when it reacts with a base. Let's get our pen back. Okay. Now, acids as proton donors. Basically, the Lowry-Bronsted theory, it defines an acid as a substance that when we put it in water will donate a proton to a base, which is our proton acceptor. Okay, so it acts as a proton donor. An acid acts as a proton donor. All right. So when an acid molecule is in water, it ionizes, and this releases a proton, which is the same as this, by the way, a hydrogen ion, a hydrogen plus ion, so it's lost its one electron, is essentially just a proton. So when an acid molecule is in water, it ionizes, this releases a proton and gives a negative ion. It also means that before it is in water, so just the pure acid molecule, it on its own needs to be considered to be neutral. Okay, so the proton or hydrogen ion is donated to a water molecule, and this forms the hydronium ion. And it looks like this. So we've got our H plus here. We add it to the water, and it gives us a hydronium ion. Now there's an example. Okay, so here's our hydrochloric gas. It is bubbled through some water, and it gives hydrogen chloride gas, and it ionizes. It's an ion donor, which means if we go HCl gas plus water, gives us a hydronium ion plus a chlorine ion. Now, in this one here, that means we've defined that as an acid, and we've defined this one here as a base. So in this, and this is what we call conjugate bases, and we're not quite there yet, but that means that is a base in this whole setup. So as I said before, it's dissolved into the water, the acid molecule is neutral. So types of proton donors, this is pretty straightforward. Basically, you've got monoprotic acids which donate one proton, so monoprotic. There you can see there. You've got diprotic, a good example, that should be a 2 down there, but there's 2 hydrogens there, so 2 protons. So sulfuric acid will donate 2 protons. And we've got triprotics, which can donate 3. Citric acid is the good example of that, which we will use most commonly. All right, but here we go. So here's a couple of examples. We've got the hydrochloric acid plus the water gives us these. Now these should all have, I'm just going to write the states for one of them, and that is the acids. So we come here, no, that one there's a liquid. Nitric acid, I think, is a solid, and that one, unsure. We'll go to liquid as well. So, but we can check those. Maybe you can check those if you want. And that's basically it. We can see here that sulfuric acid is indeed a diprotic, and we can tell that it's diprotic because this ion here still has that to donate again. So that one will then progress further to 2H3O plus and sulfate ion. There. All right. Now we need to get a couple of bits of our terminology correct, and those are the strong, weak, dilute, and concentrated. So basically, a strong acid is one which dissociates. Dissociates is where, see how the two ions have separated? It dissociates completely in water when it's forming its H plus, its proton. So a strong acid dissociates completely, which means a weak acid is one that only partially ionizes. And we see that here. So here's a strong acid, they've all separated. You'll see that there's, there should be the same amount. And here we've got a weak acid where it's pretty much just these two. So that one is ionized, and that one's ionized. But these guys have stayed together. So that's a weak acid. So a strong acid completely dissociates or completely ionizes. A weak acid partially dissociates. Now, concentrated acids, this just means that you've got a large number, so a high level of moles per liter, a large number of molecules in there. Dilute obviously means you've got a small amount. Now that is completely independent of the term weak and strong. They are completely independent of one another. And just as an example, we can use our eraser. Here we have a strong acid and a concentrated strong acid. So dilute strong acid, concentrated strong acid. A dilute weak acid, and we've still got the HB, and here we've got a concentrated weak acid. And you can see that there are still some H's and B's in there, or H's and B's in there separate. This is a good way of looking at it. So after when we dilute the pair of them, we ionize them, we see that the weak acid only goes through a little dissociation. So you've still actually got quite a lot of the acid molecule in there, and some hydroniums and whatever the A is on the back. And a strong one, we can see there's just complete dissociation. So you've got equal number of molecules of each, and you'll see that this one here, it has an equilibrium style. And this is where equilibrium really comes into it for for acids. It has an equilibrium style arrow, whereas this one just has a standard arrow because it goes completely to 100% dissociation. Alright, and here we have just some relative strengths. This is just so we can see that hydrochloric acid is indeed a strong acid. Phosphorus acid and phosphoric acid are also quite strong, and also would be triprotic. Hydrofluoric acid, as we go down to neutral stuff. And then we get into our hypochlorite, ammonia, right down to anything with a hydroxide on it. Right, so a bit of acid comparison. These are our three we're going to look at, and we're going to do this fairly rapidly. So we've got acetic acid, citric acid, hydrochloric acid, sulfuric acid. These are our formulas: C3COOH, C6H8, and so forth. These ones you've seen before. The IUPAC name, okay, so this is hydrochloric acid, sulfuric acid, but these are organic molecules. So this is ethanoic acid, and here we have 2-hydroxypropane, 1,2,3-tricarboxylic acid. All right. Now, you're not at the point where you should be able to draw it just from the name, but once you've seen it, you should. Once we've drawn it here, you should see if you can identify each of the functional groups. These two are weak acids. They actually dissociate fairly poorly. Whereas these two are extremely strong acids, and this is our standard. This is the one that we call a strong acid, is hydrochloric acid. Okay, so let's describe them. They've all got roughly a fairly strong odor, and they're sour to taste. So acetic acid is a colorless liquid with a strong odor. Citric acid is a white crystalline solid, so it's a solid at room temperature. Hydrochloric acid is a colorless gas. And the acid itself is colorless. So it only forms an acid when it's dissolved into water. And sulfuric acid is a thick and colorless liquid. It is a very, very viscous liquid. So where do we find them? We basically find them in vinegar, citrus fruits. And this one lives in the mammalian stomach, or our stomach, and is produced industrially. And this one we see in acid rain, which we've talked about already, as well as from industrial production. Here's our acetic acid. So this is what, that's not right. there should be an extra C there. All right, so that's what acetic acid. Put an extra C on there. Interesting. Anyway, I'll check that one and we'll go over it in class. Here is our citric acid, okay, and you've got the three. These are your carboxylic acids, and the three of them, the three carboxylic groups, means you have three protons to give off, and this is what makes it triprotic. And there's our sulfuric acid. That's what that looks like. We've actually seen quite a lot of hydrochloric acid, so I'm not too stressed about putting that up there. All right. Moving on to something a little bit different, we're going to look at pH as a measurement. This table is super interesting. Now, remember the square brackets mean concentration. So there's concentration of hydrogen ions, concentration of hydroxide ions. Now we see at P0, a pH of 0, we have basically a 1 molar concentration of the H plus ions. Okay, here we have a 0.1 molar of H plus ions, and so forth, all the way down to we start to get to a 1 molar concentration of what is essentially the OH ions. Now, what you'll notice is this is a reciprocal scale. Okay, when we multiply them together, they always equal 14 or minus 14. Now, okay, so it's always 10 to the minus 1 times 10 to the minus 13 gives us 10 to the minus 14 in every one. And here is pH 7. This is water. And you'll see that it has 10 to the minus 14, and it has an equal amount of hydronium ions or free hydrogen ions, and an equal amount of free hydroxide ions. Okay, so basically we use the pH scale to compare the concentration of the hydrogen ions. You could have a POH, and it would be the opposite scale. It would be a reciprocal number. Well, actually, that's not true. It would be this part here would be the reciprocal. Following table relates to the pH, relates pH to the hydrogen ion. Okay, so basically this table over here shows you how pH relates to the hydrogen ion concentration. That's pretty straightforward, and where it gives us the pH value. So in water, okay, this is roughly the same. Well, it's exactly the same. And if the ionization constant, which we'll talk about in a later topic, for water is, so it's Kw equals that. Basically, that times that. So it's always 1 times 10 to the minus 14. Now, basically, in pure water, these guys are equal. Okay. There is a small amount of ionization of standard water, of water. Water goes through a small amount of ionization just by sitting there, but it's in equilibrium. So an acidic solution, concentration of this is higher than 10 to the minus 7 moles per liter, and the pH is less. In a basic solution, the concentration is lower than 10 to the minus 7 moles per liter, and the pH is 7. And that's it. That was a lot. I hope you hung in there, and I'll see you in